Hi, my name is Glenn. We're going to look at some ways to use the NetFPGA soon. But before we do that, let me quickly review some networking basics. I'll provide an overview of how the NetFPGA processes packets. I hope this section will make the following examples clearer, particularly if your networking is a little rusty. IP transmits data in discrete packets. A message to be transmitted between two computers is subdivided and placed inside one or more packets. Each packet contains an IP header and the data being transmitted. The Internet itself interconnects many different networks, which use different underlying networking technologies, such as Ethernet. IP packets themselves are carried within the payload of packets in the underlying network. Recall that the NetFPGA has Ethernet ports. As a result, the IP packet is encapsulated inside the payload of an Ethernet frame. Ignoring the underlying network encapsulation, you see here a message that has been subdivided and placed inside one or more IP packets. Each packet consists of an IP header and the section of data being transmitted. The IP header shown here is an IPv4 header. IPv4 is the version of IP in widespread use today. I want to highlight a few fields that are important to the examples and discussion of packet processing that follow. The first field I'll highlight is the version field. This is a short field that is found at the beginning of all IP headers and indicates the version of IP in use. This field is set to the value 4 in the case of an IPv4 header. I'll next draw your attention to the source and destination address fields. These fields indicate the source and destination of the packet. Next is the time to live or TTL field. This field helps to ensure that packets never circulate endlessly within the network, even if loops accidentally occur. The TTL field is a counter that is decremented by every router that processes the packet. To avoid loops, forwarding is stopped if the counter ever reaches 0. The final field I'll highlight is the header checksum. This field is a checksum over the other fields in the header. Devices receiving the packet can use this field to verify that the header has not been corrupted. Let me now explain how data is forwarded within the Internet. I'll present a simplified model of the Internet, in which we have hosts, which are the computers connected to the Internet, and routers, which are the elements within the network responsible for forwarding traffic. What happens if computer C on the bottom left wants to send data to computer D on the top right? First, it creates an IP packet consisting of a header and the data it wants to send. The destination address field within the header is set to D's IP address. C sends the packet to the router to which it is connected, in this case router R2. Upon receiving the packet, R2 looks at the destination address within the packet to decide where to send the packet next. This decision is made by looking up the destination address in a forwarding table contained within R2. The forwarding table specifies for each destination where to send the packet next. In this example, packets destined to D should be forwarded next to R3. R2 sends the packet to the next router R3. R3 then performs a lookup using its own forwarding table. Here, R3's forwarding table instructs R3 to send the packet to R4. R4 then repeats this process, and in this case, R4 is able to send the packet to the destination D. The previous slide showed only one host communicating, but often multiple hosts wish to communicate simultaneously. The behavior is identical to that in the previous slide, with multiple packets in flight within the network. I want to spend a brief amount of time discussing how a router determines where to send each packet. Each router contains a forwarding table that indicates where to send packets for particular destinations. An IPv4 address field is 32 bits wide. This means that there are approximately 4 billion unique IP addresses. One approach that could be taken is to build forwarding tables with 4 billion entries. Unfortunately, doing so has a number of disadvantages. First, this would require a huge amount of memory to be used in each router. And while it is possible with memory densities today, it would drive up the cost of routers. Second, it may result in very costly forwarding table updates when the network topology changes. Imagine if a link fails, causing the routes to 1 million hosts to change simultaneously. IP addresses are allocated in such a way as to allow addresses to be grouped and to allow a hierarchy of groups. If all computers in a group can be reached via one link, then the forwarding table can contain a single entry for the group, instead of one for each computer. So how can we organize IP addresses as a hierarchy? IPv4 addresses are 32 bits long. Each IP address could be represented as a point on this line from 0 to 2 to the power of 32. Maybe this point here represents my computer, and this other point here represents your computer. We can be clever by allocating IP addresses in a way that lets us group them hierarchically. Let's pretend that IP addresses are allocated geographically. This section of the line could correspond to North America, and this section could correspond to Asia. We could then allocate small pieces of each region to entities within that region. For example, this small section here could be allocated to Stanford University, and this other section could be allocated to Berkeley. This geographic hierarchy of addresses can be exploited within routing tables. One entry can be used per geographic region, instead of one for each individual host. The forwarding table for this example is shown on the slide. Now that we have our IP addresses arranged in a hierarchy, how do we perform a lookup in the forwarding table? The problem we now have is that multiple entries may match a given address. For example, if a packet is destined to a computer at Stanford University, then the address matches the entries for Stanford, North America, and everywhere. This problem is solved by performing what's known as a longest prefix match, or LPM. Longest prefix match simply means find the matching entry with the most specific information. In this example, the entry with the most specific information is Stanford. We apply this longest prefix match algorithm to each lookup. Imagine that we have a packet destined to Canada. Clearly this packet matches the North America and everywhere entries, and nothing else. The most specific matching entry is North America. This is the entry that the longest prefix match algorithm would use to forward the packet. Longest prefix match can be implemented using a number of mechanisms. One simple mechanism is to sort the entries from most specific to least specific, and place these entries in a table. Linear search can then be performed using this table, since the most specific entries always appear before the least specific entries. If you look at the table on this slide, you'll see that I have sorted the entries in this manner, allowing a linear search. Other mechanisms exist that allow matches to be identified with fewer comparisons. In the preceding slides, I frequently referred to the forwarding table. Routers have multiple ports. A router needs a switching element to send packets to the correct output once the forwarding decision has been made. Routers generally contain queues or buffers. Queues are necessary to allow the router to temporarily store packets while the packets are awaiting transmission out an interface. A routing protocol runs within each router to allow it to identify the current topology of the network and calculate the best path to each destination. The routing protocol updates the forwarding table within the router. The routing protocol also generally maintains one or more routing tables in addition to the forwarding table. The routing tables contain more information about the topology than the forwarding table. Network administrators require the ability to manage routers within the network. As a result, routers contain some sort of management and command line interfaces. If we look at these components, we can split them broadly into two categories: those elements that are directly responsible for forwarding traffic, and those elements that control the operation of the router. The elements responsible for forwarding traffic are the forwarding table, the switching component, and the queues. Together these components are known as the data plane. The remainder of the components are responsible for controlling the router and are known as the control plane. The data plane must process every packet that passes through the router. The speed of the router is determined by how fast it can process packets, and the operations performed are relatively simple and uniform. As a result, the forwarding plane is usually implemented in hardware. The control plane operates at a much slower timescale than the data plane. Routing updates occur relatively infrequently, since the topology is relatively static, and management operations by administrators occur on human timescales. The control plane is also generally much more complex, at least from a control flow viewpoint, than the data plane. The control plane is implemented in software because of the timescale and complexity. In the context of the NetFPGA, the data plane is implemented as hardware inside the NetFPGA. The control plane is implemented as software that runs on the host PC. I want to conclude by explaining how the basic router components map into the NetFPGA. This is intended as a very quick overview, not a detailed discussion of how designs are implemented in the NetFPGA. First, I'll cover the data path elements, which are all implemented on the NetFPGA board. I'll start with the forwarding table. The NetFPGA designs contain an element called the output port lookup module. This module is responsible for deciding which port to forward packets to. In the case of an IP router, this is the IP forwarding table. Next, the switching component. This functionality is split between the input arbiter module and the output queues module in the NetFPGA. Together, these two modules allow packets from any input to be sent to any output. The output queues module also provides the queues that I described in the generic IP router components. Now for the control plane elements: the routing protocol, the routing tables, and the command line interface. These are implemented on software on the host PC. The NetFPGA package contains two versions of the control plane, SCON and the router kit. SCON is a completely integrated control plane. It implements all three of the control plane elements. The router kit doesn't actually implement any of the 3 control plane elements. Instead, it acts to mirror the Linux routing tables into the NetFPGA, thereby providing a hardware-accelerated Linux router.